Last time, we have seen how the martingale process like this can exist in finance. Now, this lecture does take a look at why this is significant, and let's also review what we have done to achieve that. Now, before I go on, a few words about the terminology. So you may wonder why we call this equivalent martingale measure. Well, if you have a martingale process, i.e. a stochastic process that the expectation, the conditional expectation is equal to its earlier value, it's a martingale process. Now, the probability measure under which that this process is a martingale is not unique in the sense that there can exist infinite number of probability measures such that under all of those probability measures that this stochastic process is a martingale. The word equivalent means that if two probability measures are equivalent, that means for areas where there is a non-zero probability measure, the two probability distribution are the same. They differ at areas where there is a probability measure of 0. So if you can think of that, there are infinite number of such probability measures. They only differed at the points when the probability measure are 0. Other than those places, the probability measures are the same. So that gives them equivalence. So we're not calling them the same because they differ at some places, but the places if they differ do not have significance because the places they differ has a probability measure 0. Then, so under all those probability measures, if a stochastic process is a martingale process, then basically we said there's a set of measures and they are equivalent. That's why we call them an equivalent martingale measures. Now, so let's see. So why is this significant in finance to have the martingale measures, the equivalent martingale measures, or the martingale process? And what have we done earlier? So what is significant? Well, we have seen that if a process is martingale, then the relation only is with the expectation. There's nothing else. So I briefly mentioned that in the earlier video as well, where if you have f divided by g, the ratio of f divided by g is a martingale, which means the conditional expectation of ft divided by gt, conditional upon f0 divided by g0 is a martingale, then f naught is equal to g naught times this expected value. You should know that this actually means a conditional expectation. I just dropped this conditional part of it just for notational simplicity, but you should this should be understood as being a conditional expectation. Now, so if you have this relation, you only need to worry about expectation. You don't have to worry about anything else. So you have you want to know the initial price, you know the initial price of something else, and you know this expectation, then you already have this price of the derivative asset that you're interested. So now that part of only needing an expectation greatly simplifies the way to derive or to calculate derivative asset, the prices for derivative assets. We're going to see some examples to illustrate. But before we see examples, let's just go through some of the comments here. Now, you will look back at what we have done. Basically, we have utilized some financial theories. We have determined that if there's no arbitrage, there exists a value lambda, which is really the risk price. And if we could, in our mind, thinking that we have sigma g, or the volatility of the numeraire asset, as the price of risk. And by choosing a particular numeraire, so basically whatever that you divided as the denominator, we have basically chosen a distribution under which this particular ratio is a martingale. Now, if you have a different asset as a numeraire, so it's been divided here down below, that ratio is a martingale under different probability measure. Okay, so that's why behind that, any martingale process, there's a probability measure that underlies it. So it's dependent on that. The economic theory that we utilize to derive this equivalent martingale measure, and so that to have the martingale process, is really the no arbitrage condition that allows us to derive this thing here. And the change of measure from, if we need it from one numeraire asset to another numeraire asset, depends on the mathematical principles that was behind the Gassonov theorem. Is basically the mathematical principles that allows us to change measures, change from one measure to another. Well, basically change from one equivalent measure to another equivalent measure, to be precise. Okay, now when you have a distribution, or when you have a process, let's say you have a ratio, and that, you can look at that ratio as being a variable by itself, right? So let's say that variable follows that stochastic variable follows a martingale process. You should know that the distribution that this particular process is a martingale process, that probability measure is not necessarily the real world probability distribution. And if we change the numeraire asset, you change the distribution completely. Okay, so there's so how's that linked to the risk neutral probability distribution? Well, risk neutral probability distribution is one of the distributions that we can utilize in the whole equivalent martingale measures machinery, because this is the case where if you choose a particular numeraire asset, that such that for that particular numeraire asset, the volatility of that asset is 0, meaning that that asset is like risk-free asset. So you have chosen a risk-free asset as a numeraire, and the probability measure that allows this ratio to be a martingale is a risk-neutral probability measure. But you don't have to limit yourself to that particular one. You can use any other assets as the numeraire, not necessarily the risk-neutral, or not necessarily the risk-free asset as a numeraire. So basically, the whole equivalent martingale measures generalized our way of looking at the derivative pricing methodology, where not only we can use a risk-neutral probability measure to calculate our prices for derivatives, we can basically choose any other measures, provided we have the right corresponding numeraire that we use. And then as long as we set it up the right way, this methodology will allow us to measure or to calculate or to derive the right price for derivative asset. I mentioned this before, but it's good to emphasize that it's important to keep in mind that F naught divided by G naught, this ratio is a martingale process. But F naught itself, the random variable or the random process F itself, is not a martingale process. Actually, I shouldn't have F naught divided by G naught. I should just have F divided by G. It's a martingale process, but F itself is not a martingale. So we need to be careful what we're talking about. So now as I mentioned earlier, if we choose a particular numeric asset, say you've chosen G before, so you have formed a martingale, you can always try to use another asset to be the denominator. So another asset can be used as a numeraire. Then you will have to perform a measure change. And so that you will need to do certain adjustments to change the measures. Now, you might have heard about convexity adjustment, timing adjustment, and quantum adjustment. Those adjustments basically can be explained or can be they're consistent with the change of measure approach. So we will look at those adjustments later, and you will actually see them, when we perform the adjustment, what's really behind it is a change of measure based on the change of numeric asset.